Good afternoon, everyone. I guess I need to give you a little bit of context on this talk because it's different from what you've heard earlier today and what you'll hear later in the conference. I'm not part of this community. I work on AI, and I've been recently writing a position paper on the latest developments in AI. And Yuda Pearl had access to this, and he looked at it and said, I think the issues that you address are actually similar to the ones that we've been debating in the community, so it will be useful to discuss that within this context. So I'm going to be sharing mostly remarks from this position paper. I have only about maybe 10, 12 slides, depending on how you count. And I will start by a motivation on what actually triggered my interest in writing this paper. The first one is basically this recent success that we've had in AI as far as the deployment of approaches based on what you would call ModelBlind approaches. And the speed at which it happened caused some to be concerned, and actually caused a lot of remarks that were surprising to us as AI researchers. You see some of the visible public figures and what they've said about this recently, which is somewhat, for us, disconnected from what's happening scientifically. I teach the Intro to AI course, and students tend to chase after me after class to find about superintelligence and how AI is going to take over the world, which is not how we see things. But more fundamentally, we've been asked this question more often, which is what just happened in AI, which we don't have a clear answer to. So on the one hand, you see these new applications of AI like self-driving cars and Siri and so on. But the technology that it's based on, which is the ModelBlind, or what we call deep learning or neural network, have existed in the textbooks for about 50 years. And the AI curriculum is basically almost unchanged. And so what really happened? And that's what I'm going to at least try to answer here, or what I've been thinking about. Let me also mention that there was a trigger for this position paper, which is an official quote by Yuda initially that I eventually tracked to one of his talks. So he says, the vision systems of the eagle and the snake outperform everything that we can make in the laboratory, but snakes and eagles cannot build an eyeglass or a telescope or a microscope. And it happens actually that vision is particularly the area where these ModelBlind or deep learning approaches, as we call them, have made the largest impact. That actually motivated even the paper title that I'm currently writing based on that. Okay, so I will, the next 3 slides is my take on what actually really happened. And I will start by drawing this distinction between what I call model-based approach and the ModelBlind approach. So take this particular task of what we call object recognition and localization in images. So there are 2 ways to do this. The classical way is what I will call the model-based, is you represent information about dogs, about hats, and then you reason about that in order to solve this problem. That's kind of the classical approach set by the founders of AI, and is what people would expect. The main tools for it are mathematical modeling more generally, and logic and probability. The other approach is what up until now I'm going to call ModelBlind. I'm going to change the name in just a second, is to basically solve this problem by simply fitting functions. So you have this box here. You have these inputs that come directly from the image, and you have the outputs that represent the high-level recognition you're after, and you simply learn this from data. I don't want to represent and reason. The main tool for this today is the neural network populating this box. I'll tell you just about this a little bit. But it's basically, and this is where the surprise is, the same approach that most of us have used in first or second year college when we fit simple functions like lines, x and y, but with few exceptions. Now we have many inputs, many outputs. These functions are extremely complex. I'll give you a sense of the size. But just last week, someone sent me a link from Google about a claim that you could go up to 1 billion parameters in some of these functions, just to give you a sense of the size. And instead of estimating like relations between volumes and pressure as we do engineering, we actually now estimate, we handle what we call cognitive functions or cognitive tasks. I have to say that I will be using from now on the term function-based as opposed to model-blind to emphasize the use of this black box function. And that's what I use in the paper. In fact, ModelBlind is not very common in AI as a term as it is in this community. And again, the particular approach that I'm talking about is known as deep learning. Just a couple of more words before I move on. This is what the neural network look like for people who are not as familiar. And these are basically units that simply have inputs, and the parameters are sitting on these inputs. So there are signals that are numbers that are being passed. Every unit has a bunch of numbers coming in, each number with a weight, which is the parameter you estimate from the data. And basically what you do is you take the weighted average of these inputs, and then every circle has another function that transforms that number. That's basically it. So the difference, though, that you'll see is earlier neural networks didn't look like this. They had 1 or 2 layers because we couldn't train bigger networks. And now we can actually do networks that are deep, and that's where the term comes, deep learning. It's basically neural networks that are bigger than before, and that's where the term of deep learning is. Okay, so once more, these existed for 50 years. What really happened? What allowed us to do these things? So the next 2 slides will try to answer this. And this one gives the grounds for the 3 reasons. So there's this, and then the one after that, which shows the 3 developments that I think, in my perspective, explain the current turn of events. Every function or every behavior, whether intelligent or not, can be captured as a function in the sense of the black box that I told you. You just have to look at environmental sensing as input, you look at our actions and our thoughts as outputs. The central question, though, is the following. 1, how big is that function? And second, can we really estimate it from data? I think this is a debate of, can I really represent things as functions or not? Of course. Again, the question is how big and how practical. What happened really during the last few years bears particularly on these 2 particular questions up there, and then I'm going to summarize them next. The first one is we simply know how to learn bigger and bigger functions. And that's due to 3 developments that come from 3 simple fields. One of them, the amount of data we have. Second is the significant computational power that we now have, GPUs and so on. We're talking about orders of magnitudes in just a matter of years. And third is the improved statistical techniques that we also have. All, in a sense, you can think of as marginal developments in sister fields that came together and increased the threshold of how big of a function I can actually estimate. People now talk about, I mean, just last year I would hear about millions, now I hear about billion parameters. That's one. But the interesting thing is the number 2, which I don't think people talk about. And I find it the most intellectually intriguing, is this. We now know, which we didn't before, that for certain cognitive tasks, like identifying objects and images, the corresponding functions are indeed small enough that now fall within the thresholds, number 1. I think this is we didn't know. I mean, if I were to tell you that looking at objects in an image and saying this is that and it's sitting here, we had no clue how big those functions would tend to be. And now we know. But let me just say, it's not these functions, it's reasonable approximations of them. And the 3rd development, so people don't talk about number 2. That's not part of the language. Number 3, I'm going to show you, people look at it now and say, oh, I see. But again, it's not something that people discuss, which is this. We don't build we don't build these functions or learn them. We learn approximations of them that are actually loose approximations in some cases, but we have found a way in AI or in applications to change the measure of success that we can now get away with crude approximations of these functions. Now, this is important enough that I'm going to just spend the next slide on to tell you, because it goes largely unnoticed even by core AI people. Let me give you a quick example from machine translation. One of the oldest problems in AI, and classical AI is considered to have failed on it. Now it's considered to be a success. I don't know how many of you have used Google's Translate or Bing Translate and so on. In the earlier days, when we measured success for translation, we measured against human performance. So people will take a sentence from English to Russian back to English, and if it didn't come out the same, that's failure. We used to measure success basically from how far off we are from 100% compared to a human. Now it's almost how far off we are from zero, because if you're looking at a page in a language that you don't understand, anything you get back is actually useful. That's completely different criteria. And suddenly everything looks great. In fact, if you subject these current translation systems to the tests that were traditionally subjected to, they would not be viewed as suitable at all. But they're now very useful and practical. Similar things for speech recognition. The main use of these are in user interfaces in cars, if you're trying to call someone automatically, or if you call some company for technical support, you get a voice recognition. I don't know how your experience with these. They fail and fail often. But when they do, they send you to a human operator, or they force you to do the thing manually. I personally don't use these. My wife still loves them and keeps trying and trying until she gets it right. So again, we changed the mode of operation. You can have similar examples from image recognition, where you can make small changes to images and the recognition system would fail. You deform objects in ways that humans still are able to recognize them. The systems actually fail. But again, if I'm taking a shot, a photo, and the box that is trying to find your face doesn't find it correctly, nothing really happens. You just get an unfocused image, so it's not a big deal. Again, that's something that happened actually slowly. If you look online, you'll see all kind of talks about, I didn't see AI coming. AI has come, and this and this. Really, what came are in numerous applications that benefit from almost similar AI techniques that have been just improved. They still fall short from what we hope for, but they're good enough to be capitalized on commercially. It's important. This is useful. It's good, but it shouldn't be confused with something else. And this explains this gap between this proliferation of applications and us in the classroom basically almost teaching the same stuff, right? It needs to be explained. And the reason it's important is in being able to forecast what might happen next. So a lot of these forecasts are just unscientifically based, in my opinion. And second, in really balancing research agendas. I told someone, if you work for one of the companies that is interested in some of these applications, then perhaps you should just work on the subject. But if you're interested in scientific inquiry, then the current misbalance is not justified. Let me now just make, how much time do I still have? 10 minutes, good. I want to come to another quick point, which is on the title, I used human-level intelligence or animal-like behavior. You talked about eagles and snakes and vision. You can basically look at other tasks that are tackling, like navigation and what animals can do. They're basically, we're not even close. But I want to bring this up to mention a reaction here. Someone said, what about Go? Right? So you talk about navigation and cats and speech and African parrots. What about Go? So this was in reference to I don't know how many of you have gotten this, but this was all over the news last year about Marsh. I mean, the fact that the AlphaGo system that was developed by Google beat the world champion, 18-time, I think, world champion. We all were getting calls to show up on the local news to talk about this. The reason I bring this up is the following. It is widely perceived that this is one of the other successes of deep learning, and it is actually a function-based approach, even by people who are in the middle of AI and core AI. It is not. And let me tell you why this is very relevant. This is not a neural network. AlphaGo was not a neural network. AlphaGo actually, and this point was made by Oren Etzioni, who gave a full talk about this at UCLA last spring. It uses a whole slew of AI techniques that have been under development for about 50 years, including 2 neural networks. In fact, the overall architecture was on the books. So again, because now we can build bigger neural networks, in a sense, we were able to build AlphaGo. The relevance of this is not about credit. And is it just deep learning or is it AI? For me, the relevance is, if this was a neural network, then we just learned something new about the size of cognitive functions. That a function as complex as Go that's considered in AI is more complex than chess can indeed be represented compactly as a neural network, and that's actually not the case. But again, this kind of a discussion is not part of the scientific discussion today. People are not talking about these particular issues. And the reason I also bring it to end with two more remarks is people will tell you, okay, maybe we don't have a Go function now. We can't just build it as a function. We have to compose various things to synthesize it. But what prohibits us from doing this soon? Why don't we all just continue working on thresholds, collect more data, more computation, better statistical techniques, and forget about everything else? And actually, some of the industries are doing that, maybe justifiably given where they stand. But I think this runs in two kind of quick issues. So I have basically almost two more slides on this. On the academic side, I don't see the evidence. I think anybody who wants to propose this at the academic level, industry is a different story. They have to show me the evidence that cognitive functions of interest and that are broad enough can be represented by functions of small size. Otherwise, this approach doesn't work. And we have only looked at selected applications that are driven commercially. And the second point is also important. What if we tighten the measure of success so that I'm no longer happy with the approximability that you're now doing with cognitive functions? Will these approaches still work? And by the way, history tells us to be quite cautious about this. We've done this before. We've gone through this cycle before in the 80s. We constructed functions using things called rule-based systems. They were called expert systems. We had a similar thing like now. Conferences were selling out. People introduced terms like knowledge is power, which is kind of like the equivalence of deep learning now. And at some point, we could figure out the limits of these systems and what kind of applications we can handle, and then the period after that was AI winter. Again, the transition was that we could delimit the applications. The dangerous part we're in today is we have not yet delimited the applications. That's actually fuel for wild imagination. Two more slides. Before I get to policy and considerations on why this doesn't work, let me just mention something because I think it's pretty important. It's a phenomenon I call the bullied by success phenomena. If you look in the expert system era, some of the arguments or perspectives that were being proposed there now would look as scientifically absurd. But at that time, because of the success and the dominating power of success, they actually defined scientific discussion and direction, right? Leading to what I call a bullied by success community. I saw similar phenomena during the transition from logical to probabilistic approaches in AI for common sense reasoning, where suddenly, once we started solving things probabilistically that we couldn't do logically, everybody drops logic completely. Departments that were viewed as world centers for logic stopped offering even any course. And if you look at my paper when it's out, we're paying the price now. Now we need it. We realize that logic is at the heart of probability. Anytime I assign a number, I'm assigning it to a proposition. The only difference is before I would assign it to very simple propositions. Now we want to assign them to more complex propositions than even first-order sentences. But guess what? The expertise in logic almost vanished because we stopped training people in this line of work when we actually did that transition. It's hard to blame this phenomena on anyone. There are the successful, the overwhelmed, and industry sitting in between. I just bring these remarks up because I think it's important to raise awareness about this, particularly for young researchers that they always tell me they feel somewhat overpowered to follow what is successful, even though some really don't want to do some of what is very popular, but they want to do what is right. Let me just end with a couple of slides. On policy consideration, we're focusing all of the attention only on pursuing function-based approaches. By simply pushing threshold will not work is the thing that this community probably have thought about is, and this is now being driven not just by academic considerations, but actually by real-world consideration, which is explanations. We're building systems that we need to really answer why they're doing what they're doing, and when you're doing function-based approaches, you can't just do that. They're not interpretable, and you can't answer the why questions. And this is at the heart of what we have to deal with. The good thing about this is, as I said, is driven by consideration not just academic, from society. Also, the White House initiative last year had a sequence of workshops on preparing for the future of AI. And one of the main things that were emphasized, for example, is safety. It was mentioned dozens of times in the final reports. That's putting pressure on, you can't just learn black boxes, you need to do something more. There is a DARPA program that's actually just starting next month. I'm part of this on explainable AI. People are starting to realize you have to explain what's going on. In fact, from this point of view, I'll also mention that we're also facing other challenges. In fact, a lot of us are surprised that self-driving cars are out there without going through some process of scrutiny other than someone deciding to put them out there. One of my colleagues, Eric Horfes, who's runs Microsoft Research, actually was even suggesting trials for some of particular critical AI systems, just like we do for drugs before they're employed. So even though the technology is limited, people are using it in somewhat interesting ways. Okay, let me conclude. There's a conclusion, and just one quick slide after the conclusion. I think there was something very interesting that was revealed by recent successes, but it's the one that is almost never talked about, which is what do we know now about cognitive functions and their approximations and how big these functions are. We don't even have the vocabulary. I think I used some of the terms for this in my position paper for the first time. That's not what people are talking about. We're just moving from one application to the other, one application to the other. And I really think that aside from this, the shift that you've seen is just thresholds. Data, computation, statistics. Someone who's very familiar with this, one of the main managers at the funding agency, told me it's not even statistics. He thinks it's just computational power and data that is actually caused this particular shift. And in AI in particular, I don't think the question is it model-based or model-blind, even though sometimes people make it. I mean, everybody, when they succeed, they want to make sure that their approach is the whole thing, but that's not it. It's really, in my opinion, about understanding the reach and limits of function-based approaches, deep learning in particular. The other challenge is characterizing deep learning progress in ways that facilitate its utilization by researchers outside the deep learning community. We didn't make this transition. You have to be an insider and really be in the trenches to get this thing. We don't have the definitions and theorems that you can transcend to people outside, and it's about integrating the two approaches. It's about how can I actually use the ability to approximate functions or cognitive functions at the level I can now integrate it in broader AI systems. Okay, so you're thinking, what is after a concluding slide? I was chatting to people at lunch and said, I'm looking forward to hear about what you're up to technically, and this is not it. So if you want to know about what's been up to technically, I just gave a recent talk about this 3 weeks ago at the Assignments Institute. It's on YouTube, you can look it up, but in the language of this talk, it could be thought as working on the boundary between model-based and function-based. This is not what I mentioned in the talk, but just to link to what's going on. So thank you.